that still working? Yeah? All right. Right. Hi, I'm Leo from Jane Street. I'm going to tell you about some work I did one afternoon to add semi-explicit, to add support for polymorphic parameters to OCaml. So what are polymorphic parameters? Right, so here is a function that you might write called foo, and it's a higher order function, and it takes in a function called transform, and it's going to run that first on a list of integers and then on a list of strings. And you might call such a function by passing it a polymorphic function like list.reverse. And obviously the problem with this is that if you try and do it, you just get an error complaining that that on the second call to transform is expecting a list of integers, and it got a list of strings. And that's because in classic Hindley-Milner, your type inference, your parameters can't be polymorphic functions. They have to be monomorphic. Now, in OCaml, there are ways to work around this already. So you can, record fields can be polymorphic. So you can kind of define a record with a polymorphic function as its field, and then use that to implement foo. But now you've got to kind of wrap, your call site's going to have this like wrapped record on it, which isn't great. You can do it without even having to have a type definition by using object methods. So so up here I kind of, you have foo and you have a type annotation saying that it takes an object with a polymorphic method, and then you can call it, so you can use the function polymorphically, and then you can call it with this thing. Now, obviously this isn't great either because, firstly this is very heavyweight, but in particular this type annotation here is required. And so the way that this works is described in Semi-implicit first-class polymorphism for ML by Garrigue and Remy. That system is often called polyml, although it doesn't actually call it that in the paper. And the core idea of that paper and the way that it's used to implement this is actually we're just going to be reusing that mostly. And so I'm mostly going to be talking about kind of reminding people how that works. But yeah, what we want to do is just to support this code. We just want to write a type annotation on transform, but nothing on the call site. Just be able to just call it directly. Right. Or as I said, just going to kind of reuse the underlying idea from polyml. So kind of a summary of the talk. So again, I'm going to talk a bit about the polymorphic parameters. I'm going to focus in on what I'm calling labeled types, the core technique that was used in polyml and that we're reusing here. Talk a bit about the implementation and a little bit about some related work. Right, so what we're trying to do is to support polymorphic types in parameters. So the change that we're making in terms of the type grammar is so here's the kind of classic Hindley-Milner type grammar. You've got types and you've got schemes, and only the schemes can be polymorphic, and the schemes don't appear inside of the types. And we want to just change it to this. We just want to adjust one of those taus to a sigma, so that we can have some polymorphism inside of the function arrows. It's worth noting that the equality on the schemes is going to remain the kind of ML one, so quantifier order doesn't matter, and if you have a useless quantifier, it's as if it wasn't there. Right, and so we want to make this change to the type grammar. We basically have to do two things. We're going to have to change the an introduction rule to kind of how to create functions with polymorphic parameters, and an elimination rule for how to call them. So here is the traditional rule for lambda in Hindley-Milner system, and obviously it's restricted to just having a type, not a scheme on the argument. So it's it's a type. And so if you do the naive thing and just kind of say, let's make it a scheme, that seems easy. Well, unfortunately, that doesn't work because the type inference for such a thing is undecidable. I don't want to try and describe it in too precise detail why that's undecidable. I can give you a basic idea of it. So let's say you're trying to work out, you've got for all alpha, something list to something list, and you're trying to use it as an int list to int list. And fundamentally, you kind of have two options here. You can either kind of fill in that weird x with an alpha and kind of use the polymorphism and then instantiate it down to int list, or you could just say that x was int from the beginning. And unfortunately, this kind of dilemma is equivalent to what's called semi-unification, which is undecidable. So here's kind of the traditional look of semi-unification. So you've got sigma and tau. The sigmas and taus are all kind of types, like first order terms, and you've got these. You've got this substitution S, which is kind of being applied everywhere, and that's like unification. And you've got these two different substitutions being applied just on the left-hand side, I1 and I2, and that's like kind of instantiation. And you just, the difficulty is that you can't really decide whether you should use the S or the I to solve the problem, and that decision can be undecidable in the general case. So what we're going to do is we're just going to demand that the parameter be annotated, that if you want to introduce a function with a polymorphic parameter, you just have to provide a type annotation right there on the lambda. So that one's pretty easy. The difficult bit is elimination. Because we're like, the whole point is really to do the elimination form without any additional annotation, to have the same elimination form for functions without a polymorphic parameter as functions with a polymorphic parameter. And there, the main problem you kind of run into is a lack of principal types. So here's another example, also called foo. So it's a higher order function, takes an f and a g, and the key thing is we pass the identity function to f, and then we pass f to g. And the issue here is that there are two types you could give this, and they are not, one is not an instance of the other. So either you can say that f demands that it be given a polymorphic function, and then g has to provide it with a polymorphic function if it wants to use f. Or you can say that f doesn't actually need any polymorphism, and then g doesn't need to provide a fully polymorphic function. So in one you can strengthen f and weaken g, or you can strengthen g and weaken f, and so that's why they're kind of incomparable. Maybe make it a little clearer with like some examples. So here I could pass foo a polymorphic function that uses the polymorphism of this ID, both int and string, and then g has to pass f. On this line down here, g has to pass f another polymorphic function, so it has to use ID. And so that works with the first type, but not the second. Or we could have this kind of call site where foo doesn't use u polymorphically, just uses it at int, and then g is able to take advantage of that and just provide a function that only works at int. And so that works with the second type, but not the first.
Yeah, can I ask a quick clarifying question?
Sure. Yep.
Do I need a microphone for the?
Is there one? Yeah, there's one there.
Oh, thanks. Just to say, in a lambda without annotation, which is what this original function definition was.
Yep.
There's then the bound variable is going to get a tau type. Right?
Yes.
Okay.
Yes.
But that tau type can have sigmas on the left of its arrows.
Yes. This is not a predicate.
Kind of emphasize that.
Yes.
But in just naked, unannotated lambdas, you're going to try to infer tau types with sigmas to the left of arrows. That's your goal.
Yes.
Okay.
Well, we're stretching infer there, but yes, yeah. This is in predicate. It's in predicative, not predicative. It really does let you have. Yeah, exactly. That's not too bad. It did literally take an afternoon. So, right. So the aim here is we're going to is to not infer it. We're going to you want to assume. We want to assume f is not higher rank. So given no other indication, f doesn't require polymorphism unless it is annotated. And so here's an annotation, which sounds like it's running counter to what I just said to Simon, but it's not quite. Right, so unless there is some kind of annotation some way where you know that the type requires the polymorphism. Of course, the problem is it's not enough to have information just be coming from some annotation. So here is an example. So here's the foo example, but I've inserted an if. So the old body of foo is in the else clause, and then in the if clause we kind of have an annotation telling us that f requires polymorphism. And so you might imagine that this might work. You go down the if branch and you see that f requires polymorphism, and then you get down the other side and you go, well, I must be polymorphic. But then, this is clearly order dependent, right? Like if I just flip the clauses round, it'll stop working because it won't have got to the bit where it learns about the f. Or if the type checker changes its mind about the order it wants to do things, it'll stop working. Like you really don't want to have this thing type check either. So the question essentially becomes, when is it principled to inspect some type information? When can you do this in a way that's not going to cause this order dependence? And so, right, so what we're going to do is we're going to look at this example in a little more detail and see where the problem is coming from. And so if we again, classic algorithm J, Hindley-Milner, try and type check this top one, and we go down the then branch first, we will see, when we get to the point here, where we're trying to type the call to f, we will have in our context that f is in fact a polymorphic type, and we can we have that information. But if we'd gone down the else one first, we would have alpha, and we wouldn't have had the information. And so what's happening here is Gamma is acting like a side channel. It's like smuggling some information in that you wouldn't necessarily know yet, depending on the order you've done things. And so what we really want to do is we want to know if we could tell that this function in the context and this function here were actually the same, that they'd come from the same unification variable. That's how the information had gotten to us. We know it isn't really safe to look at that information because we don't know that we would definitely have it at this point. And so what we really need is if we have some notion of identity on the type, if we know that this alpha to unit is the same as this one and not some unrelated other one that just happens to have the same form, then we can kind of solve this problem. And so what you're going to do is just kind of, so what we're going to do is we're going to put some labels on the types, on the arrows in this case. And so if you have a label on the arrow, you can kind of say, this label is the same as this label. It's not, this one is shared with the context, and so because there's this sharing between this type and the context, it's not really going to be principal to take advantage of that information. And so, right, and this is very similar to. I think it's very similar to the gen rule side condition. So in kind of Hindley-Milner, you have this. The gen rule has this side condition that says, if alpha is not a free variable of gamma, then it's safe to kind of generalize it, and in particular, it's safe to later on instantiate it and kind of do something. And one way of thinking about that condition is to think of it as saying, well, if we know that it's really, really a variable, then we can generalize it and copy it and instantiate it. We have to know that it's not secretly int, that we're not going to have, there's not some requirement in gamma that later on says, it wasn't alpha, this was just a unification variable that you didn't know that it was int yet. So it's kind of, you can think of it as a way of saying, are we done inferring this thing? Do we know everything about alpha? If alpha appears in T, doesn't appear in gamma anywhere, kind of all the constraints in alpha are known, and so it's safe to, treat that information as kind of principally known. So what we do is we can do the same thing with these labels. We can kind of extend our schemes with a notion of with a for all on labels that indicates that the label in question, which is used in the kind of squiggly sigma, is not present in the context anywhere. And we can add instantiation and generalization rules for these labels. And then we can finally write our elimination rule for the polymorphic parameter, for a function with polymorphic parameters. And the key thing here is this for all. This says if you've got a function that takes, in order to apply a function that has a sigma on the left, you need to have the label on that arrow needs to be generalized. It needs to not be shared with its context at all. Yes. Right, and so I thought there was another slide between there. Okay, fine. Right. So the other aspect of this is what happens with an annotation, and the key thing is that an annotation. So we have an annotation. You annotate a type, a term as being of type tau. You can kind of there's a type that you're type checking the inner expression with, and a type that the outer expression has. And these two, whilst they have to all agree on the kind of the bulk of the type information, they have to they don't need to agree on the labels. You can have essentially fresh labels going in and fresh labels going out, and so they kind of break the sharing between the types. And that means that when you have something like this, so when we have this annotation, we have this. So we have F and we have a type annotation on it like that. This essentially means that there's no sharing between. You get to put. There's no sharing between the type that's going on into the context with any other labels, and so you kind of get to put. You get to generalize that information, and then so when we get to the call site, it will be general. It'll be generic, and we will know that we can apply the application rule. Right. Yes. So as I say, yeah, this is. I'm calling this label type. So this is the main kind of underlying idea of the semi-explicit first-class polymorphism paper. And it's how OCaml has had polymorphic methods for a very long time. Kind of say a bit about how it's kind of implemented. So in algorithm J, unification variables are represented by mutable state. Right? Mutation is the easiest way to implement substitution. And so the identity of a variable is essentially it's kind of its physical address. That's kind of how you can think of it. And so adding labels to arrows means kind of doing the same for arrow constructors. Your arrow constructors are now mutable pieces of state. When you unify one arrow with another arrow, you have to mutate one to point to the other. And so your type expression is really becoming a graph rather than a tree. There is sharing, and you are keeping track of the sharing. But OCaml was doing this for efficiency anyway. Before PolyML, it was already doing this. Jack's nodding. Yeah. Okay. So there's already really in some efficient implementations this kind of tracking of sharing going on. And then the other aspect is kind of how do you implement the side condition. So, efficient implementation of the gen side condition that a type variable doesn't appear free in the context. Obviously, it would be terrible to go and iterate down the context and look for the variable. That'd be very inefficient. So what you do is you track the earliest position in the context that mentions the variable. So here, it's kind of like alpha is appearing over, all the way on the left, and beta appears one thing in, and gamma doesn't appear in the context. And this is represented as an offset, essentially. It's normally called a level. And so you just kind of associate this level with the variable. Like I said, the variables are mutable pieces of state. Now they have a mutable field that's their level, and that's kind of this offset into the thing. And certainly in OCaml, they use a special level infinity, essentially, although it's actually, I think, 100 million. So don't make too big a context, I guess. That represents that the variables that have been generalized. Right, and so doing the side condition on our for all, we have to do, the side condition on our application rule is basically, the side condition on our general, it means, again, putting levels on these arrow constructors as well, and tracking where in the context the arrow constructor might appear. But again, OCaml was doing that for efficiency anyway already, because if you track the levels on the constructors, you can do more efficient generalization instantiation, because you don't have to go looking for you don't have to search all the way down to see if there are any variables underneath them, because there's an upper bound of the level of the things underneath it, or possibly a lower bound. I can't remember which direction. Right, so putting it together. So yeah, the underlying facilities were in OCaml even before polymorphic methods. Polymorphic methods use these to implement labeled types. It's kind of type graph view. And this forms the basis of a lot of OCaml's features that go beyond Hindley-Milner. It's very, like, being able to inspect a type gives you a lot of, lets you do a lot of things that you might not otherwise be able to do in a kind of principle-ish way. And so, so it forms the basis of a lot of those things. There was very little to do to repurpose this for polymorphic parameters. It was, about 6 hours from realizing it was easy to do to a production-ready implementation, which we rolled out into Jane Street, and it's been used for about a year. There have been no complaints, so either it works very well or no one is using it. It's kind of hard to tell the difference. So now kind of shortcomings and related work. So the first thing is this is very much not first-class polymorphism. This is still second-class polymorphism. We have not merged the type and scheme languages together to allow schemes to appear freely everywhere. You can't have like a list of identity functions or things like that. They're just appearing on the parameter position. There is eta expansion. We don't have simple eta expansion for functions with polymorphic parameters. So if you have a function with polymorphic parameters and you write the naive eta expansion, it just doesn't type check because it's a function with a polymorphic parameter that has no annotation, so that's not allowed. You have to annotate the lambda. This bothers some people. I kind of think it's fine. Eta expansion is a typed operation anyway. It's supposed to be typed. You're supposed to do this, but yeah. No inferred introductions. So it's demanding that every polymorphic parameter have an annotation right on the lambda. So whereas you might have that information via other means. So here is like with ID that says it's going to call the function and pass it the identity function. And so here, like this won't type check at the moment for because this is supposed to be polymorphic and it's not annotated. We need to add the annotation. Now, actually, that's not what my implementation does at all. It type checks the first thing fine. OCaml does some kind of bidirectional-ish pushing around of this labeled information. But I don't think there's a formalization of it. It's not immediately obvious how to write the formal rules, so I didn't put it in here. But the implementation is kind of obviously fine. So, right. Related work. Yes, so there's kind of two groups of related work. There's kind of higher rank polymorphism work and full first class polymorphism work. So the higher rank polymorphism, there's that's where polymorphic types are only supported as part of function types, like in this. There's kind of Adursky and Laufer and Peyton-Jones et al. And that's the kind of the work that supports the rank n types extension in Haskell. There's also work by Dunfield and Krishnaswamy doing a kind of a bidirectional approach. And both of these are the key difference there is both of these are predicative. So they're not putting the sigma into the tau at all. They're adding another arrow in the sigma that allows sigmas. And so that's slightly less expressive, although perhaps not. It is a perfectly reasonable way to do it as well. Right, and then there's the first class polymorphism work. There is a lot of literature. This is a big space. I think that I kind of split it into three kind of classes. They differ mostly in how whether they infer the presence of instantiations. which is kind of the hard bit. And so the first is the group that kind of just don't infer the presence of instantiations, really. So there's QML, where just literally everything is annotated. PolyML, which is the kind of the one we've been describing here, kind of semi-explicit, and FreezeML, where you kind of indicate whether you want instantiation or not in the term language. And then you've got this second group, which is where they kind of locally infer the presence of instantiations here in the kind of like local type inference sense. So they're not doing like, as opposed to the global type inference of like Hindley-Milner. So they're doing something normally kind of, it's normally kind of bidirectional in nature, and they're looking around the application site trying to detect whether they need the instantiations. So this, so there's HMF and then this little series. These four in a row are essentially trying to get impredicativity to work in Haskell, the impredicative extension. My understanding is that Simon is finally happy with the last one, but these are yeah. But I think it is fair to describe all these as somewhat complex. There's a lot going on, especially in some of them. Then the last group are the ones where you globally infer the presence of instantiation. So that's MLF and then HML, which is just a slight restriction on MLF. And they have the kind of the most terms work. And it's very clear where you need annotations. But in order to do this, in order to do kind of global inference of whether things are instantiated, you need to extend the type language to kind of be able to represent things where you have not yet worked out whether there's an instantiation or not. And that's this kind of like, so they end up with a kind of bounded polymorphism on schemes, which is, which is perhaps complicated for the user to look at. Right. So in summary, polymorphic parameters can be sorted using the same techniques as polymorphic methods. Labeled types allow kind of a principal inspection of type information. The implementation of labeled types is similar to efficient implementations of classic Hindley-Milner. Right. That's all. Thanks.
Some questions?
Yeah, I guess I'm still a bit confused to what degree impredicative types can now be inferred, or like,
Sorry.
To what degree impredicative types can be inferred now? That wasn't really clear to me. Like, because you just seem to allow sigma to tau as a regular type, right? So that would imply that you can infer it everywhere.
You can certainly infer it everywhere where you're not introducing or eliminating it. Like once for alls are guarded underneath something, they behave pretty well. It's only when they're unguarded that you get into a lot of trouble. So it's the points where they unguard and guard that you need some kind of annotation. And on the one side, we have the introduction form where the annotation is very directly right on there. And then the other one, we're essentially doing some work to kind of only do it when there is an annotation, but the annotation doesn't have to be like right on the thing. It can be coming from the definition or an annotation and then so on.
That was kind of my other question, because I was trying to make the connection to OCaml, right, which also can handle these examples, but that has a very simple thing where you just, like, if you have a binder and you don't type annotate it, then you put in an inference variable, and that can only be a quantifier-free type, essentially. So
yeah, I mean, I think the nice thing here is that if I write a function that you can get information if you just write you don't need a type annotation if you just like write a definition that uses polymorphism and then just generalize it. You know, there's a lot of examples where you have to do fewer annotations than if you just literally say you always need to write an annotation. This is really kind of like capturing a bunch of easy cases from there. There's maybe one way to look at it. Yeah.
Thanks.
Hey Dan.
Thanks. Hey, great talk, Leo. Always enjoy your practical insights. Very nice. I want to make a little advertisement for myself, but for everyone. If you want to do impredicative inference, like the previous slide, I still think HMF strikes a great balance between simplicity and expressiveness. So I would encourage anyone to look at it. And I had a question about your previous, like one slide back. You had like the drawbacks or the shortcomings.
Oh yeah.
But this right. The no inferred introductions, that's a strength. That's great. You shouldn't try to infer like the
I like
ID5, ID6. You do infer it?
Yeah. In this case, there's some amount of kind of bidirectional type flow inside the CAML's type checker where it kind of pushes this information in, and you can kind of like when the
So if I would be DJ Remy, I would be furious now because your declarative system wouldn't capture that, right? You kind of accidentally infer something, but it could maybe rewrite it a bit, and now you don't infer it, right? So there's a risk that later, if you want to improve your
it's just
type
not,
system,
it works. It's fine. It just
It's- yeah, it's-
like there's a big difference between have not formalized and like isn't principle. It's kind of yeah. It's really it's only tricky because here the labels are kind of being treated like they're like a for all, and we're much better at doing for alls. The pushing in is a little bit like treating them like an exists. Exists is slightly trickier, but it's still it's
right.
kind of fine.
No, I'm playing
Anyway,
the devil's
that bit
advocate,
that bit was
really.
already in the compiler. You should really talk to Jacques anyway. So.
Okay, sorry. I'll give it to you.
Let me defend Leo here. So in this middle example, right, look at the call to with ID, right, and with ID's type. So with ID says what type its parameter is. So all you've got to do is push that down. There's no danger of it being unpredictable.
Yeah.
You can absolutely write these down as just bidirectional type. This is what GHC does. Completely fine.
Find the argument x, let x equals
Sure.
1 and then
So and then you then sort of generalization will happen. But yes, of course, in any bidirectional system, if you let bind, different things are going to happen. But that's different to saying it's unpredictable, right?
Yeah.
You can certainly predict what's going to happen. It just doesn't survive
really,
certain transformations.
It really is fine in practice. I know that this rule works very well in practice because whilst people don't use this very often, this is also how type-based constructor disambiguation works in OCaml. And it has that exact problem. If you lift it out of a call, you have to add a type annotation. People still just think it's great. So like it just, like you said, that transformation doesn't work.
And I agree with you too, Simon.
Yeah. All agreeing furiously, that's good. So, Leo, do you actually have the typing rules written down?
Yes.
I mean, all together on one
Yes.
sheet of paper?
I do.
Great.
I had them in an OP file, which I lost, but I have the PDF still. So as long as no one asks me to change them, it's fine.
Or the PDF to OT converter.
Yeah.
Maybe let me have it?
Oh, yeah, sure. Yeah.
I don't understand those labels
I
at
will.
all.
I will point you to where they are on the internet after this. Yeah.
Sorry. Well, I just wanted to check. So basically, is it correct that what you did was essentially polymL with the special case where the asymmetric case. So what you added is asymmetric case where you have sigma to something else.
Yes, that's
and
right.
putting the label on the arrow.
Yeah, and that lets you put it kind of lets you put the annotations kind of in the other direction than on
The
polymL.
problem in polymL is the label would have been of the sigma only, and then since it's not monolithic with the arrow, you cannot say.
Yeah. Yes, that sounds right. Yeah.
By the way, you should call it polymL.
I don't call it polymL. I mean, I did in this, but like, yeah.
That's kind of
All right. Thanks.